one result ahead, so it worked out pretty good. But let's go back to this proposition. Again, we'll talk about these localizations here. Are we multiply close? A or a fixed in this multiplicative closed set, the map given by, okay, so how's this going to work? Well, I'm tempted to say R over 1 to associate the localization, the quote fraction R over 1, but nobody said there's a 1 here in the first place. So I'm going to do the next best thing. RS is in R and S is in S, and this S is a fixed element of S. This is a well-defined homomorphism of rings. And it's got another property, and that is such that PST then the units are S for all units. B, if 0 is not an S, and S contains no 0 divisors, now let me point out in this statement here, there certainly could be 0 divisors in R. They just, none of them are in S. Then this function is 1 to 1. In particular, any domain can be embedded in its quotient. And finally, C, yeah, R has identity, and S is a subset of the units of R. So now I'm assuming that R has an identity and S is actually contained up to an R within the units of R, then Phi S is an isomorphism. Okay, so I'm not going to go over all this in great detail, but let me get you over a couple of bumps here and point out something here first. Before I talk about any of the parts here, note if 0 is in S, then RS is 0 range. That's why we usually sort of avoid this situation. But this is a silly topology. So let me say why this is so. If 0 is in S, then RS, these fractions are the same. And remember, last time we said that this fraction 0 over anything forms 0. That's pretty easy to see. And the reason for this is, of course, there is this T and S, such that T times RS minus 0 equals 0. Namely, T equals 0. All right, so if you're going to allow S in your set of denominators, then this just, you just get the 0 right. So, for part A on theorem here, what you want to, I'll leave that mostly as an exercise. I do want to show that last statement. Notice that if T is brought correct, and verify that, well, so I claim the inverse is, I think that's what you think it is. Why is this the case? Well, if you notice that well, and in fact, you don't like that, we can do this. That. Now all I have to do is show that this is the identity. So I claim for all S prime and S squared T over S squared T times R over S prime all over S prime or S prime. That's what it means for that thing function is the identity. And so this is equivalent to only if there exists a Z in S, Z comes across multiple zeros. So this is S squared T R, and this is minus S squared S prime T R. And notice that this bit in the middle is already 0, so any is equal. So in particular, this thing is a unit. What about this one right here? What about number B? Well, for B, suppose the 0 is not S and S contains no 0 divisors, then this is 1-to-1. Right? So suppose that zero, of course, what we have to do is prove that R must be 0. because we're testing kernel thing here. And let me write this one as 0 over S. Right, because I need a fraction, and I know that everything can be written over S particular S. So there exists T and R. I'm sorry, T and S. Such that T comes as cross multiple, RS squared on 0 is 0. Therefore, T times RS squared is 0. R. Agreed so far? Notice that this piece looks an S because it's multiply to the closed set and T and S are both in there. And so this is, in particular, this is not 0. Because our assumption is we don't have 0 in multiply set. So if S contains no 0 divisors, and this thing in S times R is 0, this implies R equals 0 by assumption. And so this is 1 to 1. And I'll let you check C. It's not too difficult to see. But basically what happens is if R has an identity, let me point out really quickly here that phi S of R, you can think of that as R over 1. Because now, instead of RS over S, you can think of this as equivalent to this. The S is canceled because there actually is, honest to goodness, a 1 in there. And from there, you can just show that this is, in fact, this is just the inclusion map. And is also onto it because of the assumption. Yes.
For that part B, would it make a difference if you're assuming like S contains no 0 divisors versus R containing no 0 divisors?
Oh, if you say R contains no 0 divisors, that's a stronger statement.
Right.
That's a sweeping statement. And so if you say R has no 0 divisors, then S doesn't, right? But this is a tighter condition, right? Because there may be 0 divisors in R, but as long as your set doesn't get any of them, then you're good to go.
Okay. So over here, like R is not necessarily in S, but because R multiplied by something in S is 0, and the thing in S is not 0.
That's right. So if this is not 0, which we know, and this times this is 0, then that would mean that this thing here in S is 0 divisor. So that forces our.
Okay.
Okay. Any others? All right. So in the next theorem, we're going to say, so what we're going to do now is that there's going to be a number of theorems that we do that basically explain, as you might guess, how ideals play, right? What's the relationship between ideals in R and in R localized S? So here's kind of the first warm up. Let S be a multiplicatively closed subset of a commutative ring R. R is just a commutative ring. If I is an ideal of R, then S inverse I. And I think the notation here is pretty suggestive. This is a set of things that look like this. Is an ideal of RS. B. Now here's some properties that these enjoy. If IJ in R are ideals, Roman numeral 1, S inverse On the number 2, S inverse. That. And it also behaves well with intersections. So we have those 3 properties going for us. I'll let this one for an exercise as well, but let me kind of sketch a little bit of it. Well, notice that S inverse I is certainly an abelian group. How do I know that? Well, because in the strictest sense of the word, I itself is a ring. And so, well, actually, let me be a little bit more careful with that, because you have X, Y, and I, F1, S2, and S, and X, S1, S2, S2, Y1, S1, S2. This is in S inverse I because my denominator is still an S, good to go. And the numerator is actually an I because I is a vacuum cleaner and it sucks in the S1 and the S2. Now, how about the idea of a whole ring? That is an elementary consequence of the way we multiply these things. You set that right in there. This is also in S inverse I because Rx is an I. For this one, actually, let me show number 3. Number 1 is actually 1 and 2 are not too bad. Let's do some set containments here. Let alpha over S be in S inverse I intersect 10. That is to say, alpha is in I intersect 10. S is in S. Like that. Well, notice that alpha over S is in S inverse I, and alpha over S is in S inverse J. So I've got that contained. The other containment alpha over S is in S inverse I, S inverse J. Now, what does this mean? So alpha over S is in S inverse I. And alpha over S is in S inverse J. And by the definition of these sets here, that means alpha is in I intersect J, and that'll take care of it for us. Okay. Now this next lemma, though, I think we need to pay a little attention to, because from it, there's a lot of kind of good stuff that comes out of this. Any questions on this? Let me know. 5, 9. And we'll say that S and R is more. So, then S inverse I is equal to S inverse R. So here. S intersect I. Not. Okay, let me make a couple observations. So, sometimes we say that the ideal I blows up in S inverse R because S inverse I, notice I might be, I usually think about being a proper ideal, right? Now, if I is a proper ideal, under what circumstances is this spoiled for the whole ring here? It's not proper up here anymore. This happens if and only if I actually overlaps S. This is a thing we see coming up, prime ideals and so forth, right? So this is kind of an interesting connection. Let me point out what happens here if your set S contains 0. Well, if your set contains 0, this thing blows up to 0, right? We just pointed that out. And so every ideal, so you get this equality here. And notice, what happens if your set S contains 0, then this intersection is never empty, right? Because if S contains 0, this has to have some overlap because every ideal I contains 0. So it's kind of, I think it's kind of useful to note that. So let's prove this. Suppose first, S inverse I equals S inverse R. In particular, here's where I use the ring has identity. What this means is S inverse I contains the identity, which I will abuse the notation called 1. Since the ring has identity, you can think of this as 1 over 1, because 1 would be in that right. So 1 is in the set S. You can assume that. So let's do that. And so what do we get from this? So there's an element T in S. So there exists an element T in S and X over S and X over R, or such that P, let's say 1. And what do I mean by this? This means that this is equivalent to 1 over 1, right? Which it's easy to see that 1 over 1 functions as the identity here. So that means that x over s is equal to 1. So my cross multiple is x minus s, like, and so this is equal to 0. So that means that Tx is the same thing as Ts. Oh, this is actually S inverse I, actually. Yeah, so I want x to be an I. This is an S, because T and S are an S, and this is also an I, because Tx is an I. So in other words, if these two are same, then S and I must overlap. In particular, in that element there, we have. On the other hand, now suppose that you have some element in other words, not empty. Notice that notice that 1 over x is an element of S inverse R because x is assumed to be an S, so it is an acceptable denominator. And of course, 1 is an element of the ring. Therefore, x of 1 over x is in x times 1 over x is in, well, is equal to 1. Therefore, and actually, I'm a little sloppy here. I probably should have written 1 over 1 there and written x as x over 1. But that's the gist of it. Okay, any questions? Okay. Here's another kind of bookkeeping lemma before we talk a little bit about localizations and some particular multiplication sets that are important. Proposition. An arbitrary commutative identity, an ideal has multiple subsets. And S and R multiplication of a closed subset. I is contained in, well, let's take S inverse I. And let's look at B sub S inverse. So if you take whatever S inverse I is, you would put the image of it. Then I is contained in that. B, if I is equal to the preimage of some ideal J, where J is an ideal actually in RS, Then S inverse I. Okay. And finally, if you have a prime ideal of R, and if you have the prime ideal, this is the set S, then S inverse T is a prime. Of S. And you actually get equality on that. There's a typo in the notes. It's the inverse. Okay. Pretty, let's quickly outline this a little bit. This was pretty easy. If alpha is an I, then PS alpha is alpha S, which by definition is an S inverse I. Therefore, alpha is in pre-image. So there you go. A, B, if I is equal to PS inverse, well, notice that let's give you an ideal. Let me point out something. And right, and P from R to a homomorphism. No. So let me make a more general statement here. I'm going to prove that the inverse image of any ideal of a ring is an ideal in pre-image, right? Which is actually much more general than this, and then I'll fix it up here.
I just these were T.
It's a generalization of, it's just any ring, right? Not just S inverse R, it's just some ring.
Okay.
Right, so I'm making a general statement that if you have any ideal of any ring, if it is a homomorphism from R to T, then pre-image of that ideal is an ideal of R. And actually, it's quite easy to prove this more general statement. X1, X and Y, J, say, B of X, Y, okay. Actually, the first thing I should note before I stampede off is, let's note 0 is in P inverse J. Right, because phi of zero is zero, because it's a homomorphism, which is in any ideal that you want. So I guess I should have said that at first to make sure that this is not the empty set, but we're good to go. Notice that phi of x plus phi of y, which is the same thing as phi of x plus y, is in J. Therefore, x plus y is in phi inverse. Okay, so it's closed under addition, and now all we need is vacuum cleaning treatment. Do I need on here? Now let R be an R. And X be inverse. Okay. So phi of X is in J. That's what it means for X to be free. So phi of Rx equals phi of R, phi of X, J, goes back to J as an ideal of phi. Therefore, Rx is in phi inverse. Okay, so I proved a more general statement here, and that is the pre-image of any homomorphism is an or the pre-image under a homomorphism of any ideal in any T is an ideal in R, and so particular works here. So all we have to do now is show under the situation that S inverse I equals J. So now we need to show and here we know that I is defined as the pre-image. Okay, so let's do a couple of things. Here, alpha's 9. Yes. We want to show that it's in J, right? Well, notice so we have alpha over S is in S inverse I. We know that I is the preimage J, so there exists a Z in J such that PS alpha is Z. That is to say that Z is alpha S over S. And our goal here is to show that alpha over S is in J. We know this is J. So alpha S over S squared which is the same thing as alpha over S. Because again, what you can do is the Z is already an element of J. You can divide that by alpha again, or I'm sorry, by S again. And that's still an element in there, which is equivalent to the one we started with. On the other hand, what you want to do is show that anything in J can be written in this form. So let C be in J. Well, we know that, I don't know much, but I know that Z is equal to Y over S for some. Now, I claim that the Y is in fact in I. Notice that there exists T and S such that since 0 to 1 is Y over S, P times SZ minus Y is equal to 0. So that means that in this ring, let's see if I can do this right, TSZ and notice that Y over 1 is the same thing as SZ TSZ. So Y is in so of course my goal is to show that Y is in I. That's what we set up for. So notice that TS TY TS TSZ right, so what we need to do is show TS. This is actually in J. So this is TSP, TSY. This one doesn't matter so much. So notice that PSY now you may wonder how I could do that, but remember, T is an element of S. And so remember, from our previous theorem, that means that PST is actually a unit up here. So I can invert this because T is an S, the image under PS is actually a unit. And so this thing, this is in J, this is a unit, so this is an element of J. Therefore, Y is in I, and we're done. We've got the other thing. I will leave the last part as an exercise, but let me point out something about B here. Note that every ideal of S inverse R of S, which is what I usually write it, is of some ideal INR. And this is why, because all you have to do is take your favorite ideal in J, look at its pre-image, which we proved in part B. Pre-image is always an ideal. Part B says that your original J is of this form. So any ideal J that you find in the localization is S inverse I for some INR. So there's a correspondence there going on here. So here's a follow-up to that. And this one's a biggie right here. Let R be commuted with identity S multiplicative of the closed subset. Closed subset, then there exists a one-to-one correspondence between prime ideals missing S and prime ideals are localized. So here's the way it works. That's what I mean by missing S, not that it's heart is lonely, it's just the intersection is empty. And here's the way the correspondence works. And you can get this back. The only thing that you have to check, which I recommend that you look at for an exercise, is show that the prime property is preserved. The correspondence you can get pretty easily, but the prime property being, and also S inverse B, you'll need that this happens for prime ideals. So you'll need prime to show that you actually get an equality here, and also the prime property is preserved. Okay. So I'm going to leave you with one last result for the day. First, I need to give you a notational definition, which is, it's unfortunate, I'm sorry, but so I'm going to call it strange notation. And it's industry standard. Let R be a ring and let P a prime ideal. The notation of P is actually, what this means is R localized S with S equal to the complement of P. Yeah, it really stinks. Right, so R sub P is a set of R over S, where S is not in. Yeah, so when you see the subscript is a set, that means that's a set of denominators. When you see the subset is a prime ideal, that means it's everything that's not in there. And I apologize on behalf of the community, for that. So here's the last corollary, previous. I 12, let R be commutative with identity and P is prime ideal. Number one, there is a one-to-one correspondence between prime of R localized P and primes of R continued P. This is often called R localized at P, just like the notation for sets. So actually what happens when you localize a P is you only retain the primes that are contained in the original prime P, and P localized P, which is a set of P over F, where F is not in P, is in P, is a unique maximal ideal. So see if you can verify. I mean, the correspondence shows that that's the unique maximal ideal of that. So when you pass this, what happens is you only leave the maximal ideal P. P is the unique maximal ideal in the quotient. Okay, any questions? Any questions? All right, well, y'all have a good one. We will see you on Friday.